So in this problem, we're going to find the potential inside and outside of a sphere with a constant potential on the surface. So these are the formulas for the inside and outside potential. I'm not going to prove this. You can find this in the examples. So let's try to find the inside potential first. So we know that on the surface of the sphere, so this is the inside potential. So we know that when the small r is equal to big R, so when you're on the surface of the sphere, this is equal to a constant, so this is given to us. So now we're going to apply Fourier's trick, so we multiply both sides by a Legendre polynomial, and then integrate it from 0 to pi. And then we're going to do the same thing to the left side, so we get AL prime, RL prime, and then because of Fourier's trick, we have an expression like this. So once again, I'm not going to prove this. You can find this in the example. So now we can actually notice that we can write V0 as V0 P0 cosine theta, because the zeroth Legendre polynomial is actually just equal to 1. And so by the because of the fact that Legendre polynomials are orthogonal, we know that all the a terms, all the way from a1 to a infinity, they're all going to be equal to 0 except for a0. So a0 is the only case where the orthogonality does not get rid of this term over here. So the only term that survives is a0, and we're going to try to find out its value. So r to the power of 0, that's equal to 1, 2 over 0 plus 1, that's equal to 2. So let's pull the v0 out. So essentially, once again, we have another Legendre polynomial, and then the square of this, from 0 to pi, you just arrive at this expression again. And then in our case, L prime is equal to 0, so actually just cancels out with that. So now you see that a0 is actually equal to 0. And so going back to finding the potential inside of the sphere, so applying the result that we found, so only a0 exists. All the subsequent a constants are all equal to 0. So if a0, r to the power of 0, that's 1, and then p0 cosine theta, the first Legendre polynomial, that's also equal to 1. So actually, the potential inside of the sphere is equal to a0, which is equal to v0. So this tells us that inside of the sphere, the potential is the same as the potential on the sphere. So the inside is the same as the surface. And you know that that's true, right? Because that conforms to the conclusion we have from shell theorem. So all this makes sense. So for the next step, let's try to find the potential outside of the sphere. And then to do this, I'm going to use a continuity argument. So we know that both of these functions must form a continuous whole. So once both of these functions meet at on the surface of the sphere, so when small r is equal to big R, and at that very moment, the inside must be equal to the outside. So we know that on the surface of the sphere, this must be true. And so by comparing coefficients, so let me just write out the expression. So by comparing coefficients, we can actually come to the conclusion that BL over RL plus 1 must be equal to AL RL. So BL must be equal to AL R 2L plus 1. So we found this conclusion. And then we know that A1 all the way to A infinity, they're all equal to 0, right? Only A0 exists, and that's equal to V0. So that's why only B0 exists. All the B1, B2 all the way to B infinity, they're all equal to 0 as well, because of this relationship. So now we arrive at this conclusion, and so we get this result here, that's equal to B0. So returning to the original question, what is the potential outside of the sphere? So once again, we write out the expression, and then B1 to B infinity, they're all 0, so what we have is B0. When L is 0, it's just R. P0 cosine theta, that's just the first Legendre polynomial, which is equal to 1, so we only have this. And then B0 is equal to RV, right? So there we have it. This is the potential outside of the sphere. And this is the potential inside of the sphere. And then you see that it all makes sense. It conforms to everything we know about shell theorem. It's constant inside of the sphere, and it's proportional to whenever r outside of the sphere.